Hi, welcome to my channel. I am Aravindan. In this lesson also, I am continuing discussing Cambridge past paper questions related to electric field. In the previous video, I discussed the same worksheet, questions 1 to 4. In this video, I'm going to discuss question 5 onwards from the same worksheet. All the questions are collected from the Cambridge past papers, different years. The worksheet is uploaded in the Google Drive and you can download it before watching this video. The instructions are given in the description part of the video. The link also given in the description part. So go to the description part and get the proper link. It's there mentioned and download the worksheet. Okay, question number 5. Already I discussed 1 to 4 in the previous video. Okay, question number 5. They are saying there are two spheres A and B kept in space and the distance between the centers of the spheres is 20 centimeters. And there's a point P which is measured from the center of A and its distance is x. The radius is 1.5 centimeters. Okay, and also they are giving this graph how the electric field strength, that is the net field strength. Okay, both charges are carrying, both spheres are carrying charge, but they are not carrying same magnitude of charge. They are carrying different magnitude of charges. So how the net electric field strength varying in the region between the two spheres are given by this graph. Okay, so you can see the electric field strength below this is 0, means that is this value. If you read it from the graph, that value is almost I think, yeah, 1.5, I think, yeah, 1.5 it should be. So you can see inside the sphere electric field strength is 0, right? So they are saying two solid metal spheres A and B, each of radius 1.5 centimeter, are situated in a vacuum. Their centers are separated by a distance 20 centimeter. Both spheres are positively charged. Point P lies on the line joining the centers of the two spheres at a distance x from the center of the sphere A. The variation with x of the electric field strength E at point P is given on the graph, right? Page number 6, I am moving now. Page number 8, sorry, page number 8. There the graph is given. Use figure 6.2. So this is named as figure 6.2 in the worksheet. 6.2 to determine the ratio of magnitude of charge on sphere A or magnitude of charge on sphere B. So that is, they are asking to find they are asking to find charge of A over charge of B, how much? That's the first part question. Okay, that's easy. So from the graph, you can see this. I didn't mark all the values when I drew it on the board. You can get it on the graph when you download the paper from the description part. You can see at 11 centimeter x, when the x is 11 centimeter from the center, the electric field strength is 0. That means at that point, the electric field strength is 0, means it's a null point. So I can say at that point 11 centimeter electric field strength is 0, means I can say, so this is the question, so I'm going to find it. I can say E1 equal to E2 at 11 centimeter from the center of A, is it? That is 20 centimeter, that's distance between the two spheres. So I can say QA over 4 pi epsilon naught R1 square is equal to QB over 4 pi epsilon naught R2 square. R2 is the distance of that point from the center of B. Okay, so 4 pi epsilon naught, 4 pi epsilon naught get cancelled. Or you can use KQA, KQ R square, anything you can use. Okay, so now I'm going to get QA over R1 squared is equal to QB over R2 squared. So QA over QB is the question. That is R1 over R2 all things squared. R1 square over R2 square. I can say R1 over R2 all things square. R1 is the distance of that particular point where the null point occurs from A, that is 11. So 11 over, okay, that is 11 over 9, because this is 20, this is 11 means that is 9, 9 all this squared, solve it, you will get the answer that will be equal to 1.5. Okay, the same part I can answer by using these two values also. This is the electric field strength on the surface of A. This is the electric field strength on the surface of B. So beyond it, it suddenly becomes 0 beyond it. So that is the surface of B, right? So the electric field strength at the surface of B is 32. So you read it from the graph, right? So I can use that information to find the same answer. See, we'll check whether we are getting the same answer. I can say electric field strength on the surface is given as E equal KQ over R squared or Q over 4 pi epsilon naught R squared. Right, both have the same radius, 1.5 centimeters. So I can say KQ over R squared, is it? That is on the surface on the surface. So, okay, the electric field strength for A, on its surface is 48. So I can say 48 equal KQA over R squared. For B, the electric field strength is 32. So 32 equal KQB over R squared. Both have same radius. They are giving it also, it's shown on the diagram. So divide equation 1 by equation 2. I need QA over QB. So if you divide, K will get cancelled, R squared will get cancelled. So QA over QB equal to 48 over 32. That also 1.5. So either way, you can answer the same question. That's the A part of question 5. Okay, same question, question number 5, part B, page number 9. You can download the paper from the Google Drive. So just go through the description of this video. There all the instructions are given how to download this particular worksheet. All questions are from Cambridge. Okay, so question 5, part B. The variation of potential between spheres A and B is given. So you can see that up to the radius, constant potential, varying, then constant potential up to point, the center of the sphere B. Right. They are saying it, the variation of distance x of the electric potential V at point B is shown on the figure 6.3. So this named as figure 6.3. Right. An alpha particle is initially at rest on the surface of sphere A. The alpha particle moves along the line joining the centers of the two spheres. Determine for the alpha particle as it moves between the two spheres its maximum speed we need to find. That is B part, first part, question number 5, B part, first part, we need to find the maximum speed. Okay, first you should know what is alpha particle. Alpha particle is the helium nucleus. So its charge is plus 2 times charge of an electron. It's a positive charge. So charge of alpha particle is 2 into 1.6 10 to the power minus 19 Coulomb. And it consists of 2 protons and 2 neutrons. Mass of proton is almost equal to mass of neutron. Mass of proton, neutron are given in the data sheet 1.6 10 to the power 9.11 10 to the 1.67 10 to the power minus 27 kilogram, 1.66 10 to the minus 27 kilogram. Yeah, it's given in the data sheet. So mass of a helium nucleus is 4 times the mass of a proton, right? That is not a problem. You can get the data from the data sheet of the question paper. I didn't put those things. You can get it in the actual question paper, the data sheet. Okay, so they asked to find the maximum speed. Okay, so it's released from rest. So you can see that it's moving from higher potential to lower potential, high potential to lower potential. So the potential is varying like this. So this is the potential of sphere A. You can see that potential is decreasing, then increasing, but it's not coming to the same level. So they ask him to find the maximum speed. So maximum speed occurs when there is maximum work done on it, is it? So whenever there's a maximum work done by the electric field on the alpha particle, is a positively charged particle. So whenever there's maximum work done on it, it will get the maximum kinetic energy. That will be the maximum speed. Right. So when it moves from surface to this point, the potential difference will be maximum. If you find the potential difference, this potential minus this potential, so the potential difference is going to be a negative quantity. So work done is going to be a negative quantity. So I told that whenever work done becomes negative, the particle will gain kinetic energy. Is it? So I can say work done is equal to Q times delta V, right? So that is going to be charge is alpha particle 2 into 1.6 into 10 to the power minus 19. Delta V, the change in potential 0.18 minus 0.76. You will get a negative work done. That means the charge particle, the alpha particle, is going to get or gain kinetic energy. So solve this, you will get the work done, which is a negative quantity. Okay, so you will get the work done is going to be a negative quantity, right? Minus 1.86 10 to the power minus 19 joule. So that means it's going to gain kinetic energy. So I can say gain in kinetic energy is equal to, this is the work done by the electric field. That's the reason it's gaining kinetic energy is equal to work done. So half mass is 4 times 1.66 10 to the power minus 27. That's the mass of alpha particle, which consists of 2 protons, 2 neutrons, into V squared. Initially it was at rest, so initial kinetic energy is 0, equal to, when you use this, use the magnitude 1.86 10 to the power minus 19, solve it, you will get the speed that is going to be the maximum speed, because I consider the maximum potential difference. That's the reason. Maximum potential difference gives the maximum speed. Okay, when this becomes maximum, delta V becomes maximum, work done will be maximum. When the work done is maximum, speed will be maximum. And also this negative sign shows when it is released, it's going to gain kinetic energy, lose electrical potential energy. So you'll get the speed equal to 4.6, 7.5, 10 to the power 3 meter per second. Okay, those who are not interested about identifying the minus sign, whether you are not interested about whether it's gaining or losing kinetic energy, just if you want to write QV equal half mv squared minus half mu squared. But I don't want to teach like that, because that shows, this method shows whether you are whether the charge particle is gaining or losing kinetic energy. But those who are not interested about that one, you can just write half mv squared, that's a final kinetic energy, initially is 0, equal Q times delta V, find the magnitude of it. Okay, don't consider positive or negative, just do it, you will get the answer. But I feel this is better. It shows whether it's gaining or losing kinetic energy. Okay, next part, that is part 2 of B part, second part, page number 9. Find the speed on reaching the surface of sphere B. Okay, when it is at this, when the potential becomes 0.54 volt, what will be the speed? Okay, you can do, since you know the speed here, you can do from here to here. So when it moves from here to here, look at here, it's going to the potential is increasing. So the final potential is larger than initial potential. So work done is going to be positive quantity. So work done is going to be positive quantity, means certainly it will lose its kinetic energy. If you want, you can consider these 2 points and find the velocity, final speed if you want, or you can use these two. Compared to these 2 points, this is smaller potential, this is larger potential. So if I consider these two potential, this is the potential at B. If I consider these two potentials, I will get the final velocity which is greater than initial velocity, because final potential minus initial potential, it's going to be negative quantity. Work done is going to be negative quantity, so it will gain kinetic energy. It was at rest, so I can find the speed here. That is easier. But if you want, you can consider these 2 points and find the potential difference. I'll do both methods. This potential minus this potential, there it's going to lose the kinetic energy. I'll do both methods, but if you consider these 2 points, that is easier to answer. Okay, so I can say I consider the points from surface of A to surface of B, right? So from surface A to B, I consider. So their work done is equal to Q times delta V. So that is Q is 2 into 10 to the power, 2 into 1.6 into 10 to the power minus 19 times the potential is 0.54 minus 0.76. So here you will see the work done is going to be negative quantity. Okay, so here minus 7.04 10 to the power minus 20 joules when I consider A to B. So that means again it's going to gain kinetic energy when it moves from A to B, right? So I can say now this is the work done. It's going to, charge particle is going to gain kinetic energy. So I can say gaining kinetic energy half into the mass of the alpha particle 4 times 1.66 10 to the power minus 27 into v squared, that is the final speed. Initially it was at A, the speed was 0, is equal to the work done, that is the gain in kinetic energy, that is 7.04 10 to the power minus 20. Solve it and find the speed V. You will get 4.6 10 to the power 3. Okay, for the question number 5, B part, second part, we got the answer by considering the motion from A to B. Okay, some students, they get idea because previous part, they asked to find the maximum speed. So we found the speed at 11 centimeter from A. So some students, they try to continue the calculation for the motion from that 11 centimeter to surface B. So those who are considering that way, that you won't go wrong. You will get the answer. Correct answer will be obtained. But only thing you need to follow the proper method. So you can see when it moves from 11 centimeter to surface of B, the potential is increasing. Potential difference is going to be positive quantity. Work done, see I did it like this, work done is going to be a positive quantity. So I told that earlier. So when the work done become positive quantity, the particle will lose its kinetic energy, right? So work done is 1.15 10 to the power minus 19 joule when it moves from 11 centimeter to the surface B. And there the equation should be loss in kinetic energy, because when the work done become positive, it will lose kinetic energy. So loss in kinetic energy equal work done, right, against the electric field. So loss in kinetic energy means initial kinetic energy at 11 centimeter, that is half times mass times 7.5 10 to the power 3 all things squared. This we found in the previous part, that is B part, first part, maximum speed minus speed on the surface half into mass into V squared, that is equal to work done against the electric potential, that is 1.15 10 to the power minus 19. Careful. If you write this other way, you will go wrong. So when you solve it, you will get exactly the same answer what we got in the first method. But I feel this is easier when you consider the motion directly from A to B, that is easier. But you can do from the point where the maximum speed to surface B also, you can get the same answer. Nothing will go wrong, but only thing you need to understand Whenever the final potential becomes more than the initial potential and the charge is positive when you calculate the work done, if you get positive, that means it's losing the kinetic energy. Okay, question number 6, page number 14 in my worksheet. A part. For any point outside a spherical conductor, the charge on the sphere may be considered to act as point charge at its center. By reference to electric field lines, explain this. Okay, if you consider point charge, the electric field lines are from the charge. But when you consider sphere, which carrying a uniform distribution of charge, they are also, the electric field lines are radial like this. Inside no field lines, sorry, if I say positive charge, the field lines will be away from it. But if I extend the lines, but actually field lines is not there, but if I extend it, it looks like it comes from a point, is it? So we assume, we can imagine the field line is coming from the center where it consists of a point charge. The whole charge is concentrated at the center. We can assume like that. But actually that is the idea of Gauss law. The word Gauss law is not in your syllabus, but the application is in your syllabus. So the answer for that, you can say like this. The answer can be given as the electric field lines are radial. You can say 1 mark. Electric field lines are radial. And the field line, when the field lines are extended, they appear to meet at the center of the sphere. Okay, when the field lines are extended, they appear to meet at the center of the sphere. Okay, that's the answer for A part. Okay, B part. An isolated spherical conductor has charge Q as shown in figure 6.1. This is the diagram. And they have given the point P is movable point that at any one time it's a distance x from the center of the sphere. So that is the point P. This is x. The distance is marked as x on the diagram figure 6.1. Right. The variation with distance x of the electric potential at point P due to the charge on the sphere is shown here. So this is the variation of electric potential of variable point P from the center. You can see the shape of the graph that is named as figure 6.2 in my worksheet. Okay, so that's a variation of electric potential. So the first part of question 6, that is yeah, that's the first part, B part, first part. So this is belong to B part, this graph. So B part, first part, use figure 6.2, that is this graph. Okay, use figure 6.2 to determine the electric field strength, capital E, at point P where x is 6 centimeters. So from the graph you can read it. It's a grid. So at 6 centimeters, if you read it, you will get 5.4 into 10 to the power 3 volt. Right? So they asked you to find the electric field strength at 6 centimeter. So we know the electric potential at 6 centimeter, that is 5.4 10 to the power 3, that is 5400 volt. And they asked you to find the electric field strength. So it can be found in two different methods. Okay, first method, you know that already I told that in my previous lessons also. Electric field strength E is equal to minus dV over dx. Anyway, you don't have calculus, but you know that is the gradient of the tangent of the voltage x graph, is it? So at 6 centimeter, if I draw a tangent to the graph, bit difficult, you can keep the ruler like a tangent. If you draw the tangent to the graph at 6, you will get a negative gradient because slope is like this. But multiplied by minus sign, you will get the electric potential. So draw a tangent to the graph at 6 centimeter and find the gradient of the tangent by taking 2 points on the tangent you drew and find the gradient of it. That will be the electric field strength. So there, the answer you will get if you do that way. Mark scheme is accepting 9 into 10 to the power minus 9 plus or minus 1.2. I think 1.2, yeah. So that means 7.8 to 10.2, 10 to the power 9, they are accepting, because you know when you are drawing tangent manually, you won't get exactly the same answer. Right, that is method 1 for the finding the electric field strength at 6 centimeter. So another method also I can use the equations, right? This is method is right. Okay, that is one method. Those who like to do, draw the tangent and find the gradient of the tangent. Second method, I know that potential is given, but I don't know the charge on it. They are saying symbol Q. We know the equation for potential V equal KQ over R, or KQ over distance. So we know the potential 5.4 10 to the power 3 equal K. We know the value of K. We'll substitute it, or we can get cancel it when we divide. We'll see. Q we don't know. And the distance R 6 centimeter. So 0.06. Keep it as equation 1. The question is electric field strength, is it? So this equation when we use, we assume the charge is concentrated at the center, right? So electric field strength at that point E equal KQ over R squared. Is it KQ over R squared? That is KQ over R squared is 0.06 squared, equation 2. Okay, I think now you will get the idea what I'm going to do. Divide equation 2 by equation 1. So divide 2 by 1. That is E over 5.4, 10 to the power 3. Is it E over 5.4, 10 to the power 3? If you divide each other, equal KQ over this divided by this. No, you know KQ and KQ will get cancelled. So finally, what will be there? So I'm dividing 2 by 1. So you'll get 1 over 0.06. Is it? KQ will get cancelled. So I can say like this. You can say KQ over 0.06 squared into, this is the division. So 0.06 over KQ. So KQ will get cancelled, square will get cancelled. So solve it, you will get the electric field strength. So there also answer you will get almost 9 into 10 to the power 9 into 10 to the power 4. Yeah, 9 into 10 to the power 4, sorry. 9 into 10 to the power 4 Newton per Coulomb. Okay. So you can follow one of the method, either this method, okay, drawing a tangent method, or get the equations and divide each other. Both will be the same answer. Okay. Okay, so next part they're asking determine the radius capital R of the sphere, explain your answer. So there's nothing to calculate. So when you see the graph, you know for the sphere, the electric potential is the same at all points, same as the potential on its surface. So you can see the electric potential is constant. So if you read it from the graph, so this is the end of the radius, outside is starting beyond that. So if you take the read it from the graph, you will get 2.5 centimeter. So the radius is 2.5 centimeter. So you can say the electric, so the explanation, they are giving 2 marks. You can say well, 1 mark for the value, the other one, you can say the electric potential will be the same at all points inside the sphere. Okay, you can say the potential is constant or the same at all points inside the sphere. So from the graph, 2.5 centimeter, that is the radius of the sphere. Okay, the last question in this worksheet, question number 7, page number, I think 15. Yeah. Okay, so there an alpha particle is traveling in a vacuum towards the center of a gold nucleus, right? As illustrated in the figure 5.1. So all the information are given. Charge is 79 times of charge of electron. One is positive charge, and energy is of the alpha particle also given. The gold nucleus has charge 79e. The gold nucleus and the alpha particle may be assumed to behave as point charges. At a large distance from the gold nucleus, alpha particle has energy of 7.7 10 to the power minus 13 joules. The alpha particle does not collide with the gold nucleus. Show that the radius of the gold nucleus must be less than 4.7 10 to the power minus 14 meters. So they are saying it's not colliding. The alpha particle does not collide with the gold nucleus. Okay. So this you learn in IGCSE, the alpha particle scattering experiment. Based on that, this calculation is given. Okay, so it's not colliding, they are saying, and the energy is given. So we can say alpha particle also positive, nucleus also positive. When it moves from here to here, it's going to experience opposing force. So when it experiences opposing force, it will slow down or it will lose its kinetic energy, right? So they have to find the distance. Careful, they have to find the show that the radius of the gold nucleus must be less than 4.7. So it's not colliding, they are saying, right? So radius of the nucleus. So we'll say up to what distance it's coming and getting stopped. So when the alpha particle is moving, it's going to slow down. It's going to lose its kinetic energy. Okay, so this calculation we can't do by using equations of motion or any v squared equal u squared plus 2as. You can't use it because the acceleration is going to change, because when it moves, the force is going to change. So the only thing is work done and electric potential. Notice that they are saying the gold nucleus of the alpha particle may be assumed to behave as point charges at a large distance from the gold nucleus. Okay, careful, the word large distance from the gold nucleus means when it is at far distance, that means initially it is not in the electric potential of the gold nucleus. You know, gold nucleus is creating electric potential everywhere. So initially the alpha particle is not in the electric potential of the gold nucleus. So for the alpha particle, I'm going to use the equation loss in kinetic energy, right? Loss in kinetic energy is equal to work done against electric field. So I can say loss in kinetic energy equal to work done against electric potential. So work done is equal to Q times delta V. Okay, Q times delta V. That means Q times the potential difference we don't know. Q times delta V means, so see, this is the point where the alpha particle is stopped. So the distance of this particle from the center of the gold nucleus, let it be R, right? So at this point, the gold nucleus is creating a potential. I can say V, so that is the final point, V1, right? And initially the alpha particles what at far distance, there the electric potential is 0. I told that whenever something moving, final potential minus initial potential give the electric potential. Initial potential is 0 because it is at far distance. That word is used. So the point where the alpha particle stopped from the gold nucleus, I can say that is at a distance r from the center of the gold nucleus. So there the potential is V1. So I can say Q, the potential there, charge of the gold nucleus over 4 pi epsilon naught r, or I can say KQ over r. KQ over, I mark it on the diagram, r minus 0. This is the charge of the alpha particle. Loss in kinetic energy of the alpha particle. It had this much of kinetic energy initially. Here it stopped. So that means it lost all its kinetic energy. So loss in kinetic energy is 7.7 10 to the power minus 30. Substitute the values. Find the R. So 7.7 10 to the power minus 13. Charge of the alpha particle, you know, it's a positive charge. 2 times it's given. No, you must know that alpha particle is a helium nucleus. So 2 into 1.6 10 to the power minus 19. K 9 into 10 to the power 9, or you can use 8.99. I normally use 9 into 10 to the power 9 into charge of the gold nucleus, because this is the potential of the gold nucleus. Okay, this quantity is potential of the gold nucleus. So 79 into 1.6 10 to the power minus 19 over R. R is the point where the alpha particle is stopped. Solve it and get the value of R. Okay, you can see that the distance, the point at which the alpha particle is stopped is at a distance of 4.72 into 10 to the power minus 14 meter when you solve it. So at that point it is stopped, and they are saying in the question, careful, they are saying it, the alpha particle does not collide with the gold nucleus. So that means it stopped at this distance from the gold nucleus means, and it is not touching the gold nucleus means the radius of the gold nucleus is smaller than this value. Okay. Okay, so the next part, determine the acceleration of the alpha particle. That is the B part of question number 7. Okay, this is question number 7. A part we answered. Okay, B part. Determine the acceleration of the alpha particle for a separation of 4.7 10 to the power minus 14 meter between the centers of the gold nucleus and of the alpha particle. Okay, so that we can find by using electrostatic force between the gold nucleus and the alpha particle and Newton's second law, F equal ma. So big part I can say F equal k q over r square. R is this distance equal ma. So k I can say 9 into 10 to the power 9, 8.99 10 to the power 9, but I am using easy 9 into 10 to the power 9. Charge of the alpha particles 79 into 1.6 10 to the power minus 19. Charge of the alpha part, that's a gold nucleus. Charge of the gold nucleus. Charge of the alpha particles plus 2. So 2 into 1.6 10 to the power minus 19 divided by R. We found it in the previous part, that is 4.72. Is it 10 to the power minus 14 all things squared, that we found it in the previous part, equal to ma. So mass of the alpha particle is, alpha particle, it consists of 2 protons, 2 neutrons. So masses are almost same. 4 into 1.66 10 to the power minus 27 times A. F equal ma. Solve it, you will get the acceleration. So acceleration will be 2.5 10 to the power 27 meter per second squared. Okay, the last part, C part. They're asking the alpha particle scattering experiment, IGCSE you would have learned. They use a foil, not a gold plate or thin plate. They say gold foil. Why should it be gold foil? Means, even if you take the thickness of this sheet, right, in this thickness of sheet, there will be lot of several millions of atomic planes. So when alpha particle collides, there will be confusion which the alpha particle is colliding with how many number of nucleus, can give unwanted confusions in the calculation. So to avoid that, they use a thin foil so that can reduce the number of layers of the gold atomic planes. So we can say we can reduce the multiple deflections due to many gold atoms. Okay, so to reduce it, we should have a thin foil. So number of atoms will be, number of nucleus will be very less. So reduce the multiple deflection. Okay, so I hope that this Cambridge paper will be useful. But even Edexcel students can follow this. But Edexcel questions are slightly different. Okay, so next I'll upload a worksheet for Edexcel students. For Cambridge, if I have time, I'll upload some other worksheet. Okay, right. Bye.